Is it on? Oh, yeah, now it's on. Okay. All right. Yeah. Yeah. Thanks a lot for the introduction, and thanks a lot for the invitation to give this talk today. So, as mentioned, I'll talk about twisted bilayer graphene, and I'll try to make as general of an introduction as possible. But of course, maybe still a lot of details for people who are not really familiar with the topic. But basically, I'll try to give some overview of moiré materials and twisted bilayer graphene in general. So twisted bilayer graphene are those two sheets of graphene which are just stacked one on top of another with a random angle. I will talk about the newly observed quantum phases in this material, superconductivity, correlated insulators, and so on. And last but not least, maybe in the very end, I'll also talk about some quantum sensing with these moiré materials. And so before I go into the details, let me just introduce ourselves. So we were, until recently, and actually until still, a group in ICFO in Barcelona. So we are moving right now to LMU Munich. So our labs have been renovated, and we'll be in around a month. We'll pack up all our stuff, and we'll be heading to LMU. So we are also part of the MCQST and Munich Quantum Valley here in Munich. And also, the title of my talk was Plethora of many-body ground states, but also, as we are starting up the group right now, we also really have a lot of open positions. So if you have know anybody who's interested in master's thesis, PhD, or postdoc, et cetera, in this field, we'll be up and running really in a couple of months. So I think after October would be a good time to join. So really to start with the introduction, so the field of twisted bilayer graphene really took everybody by surprise who was working on two-dimensional materials and graphene. When Pablo Herrera in 2008 discovered that you take these two graphene sheets, rotate them a little bit, and then at a certain angle, the magic angle, you start observing all these phases, such as superconductivity, topology, magnetism, correlated insulators, and even strange metals. And really, before that, graphene was mostly explained by a single particle picture, unless you apply a really high magnetic fields and so on. So really, this took the field of two-dimensional materials really into the area of strongly correlated materials. So all of these experimental techniques which we apply are rather simple. We figured out how to exfoliate layers of two-dimensional materials from bulk van der Waals materials, so we can really prepare almost any van der Waals material you give us. And we can create single layers of these materials, really one atomic plane of these materials, and deposit it on substrates. We also figured out how to, with stamping techniques, how to assemble these materials one on top of another. And really what this allowed us to do is to sort of have extreme control of the sort of material species which we can create. So these hybrid materials and heterostructures that we can assemble superconductors, ferromagnets, Dirac materials, topological insulators, and so on, one on top of another. And while conceptually this seemed very easy at the time, what was the biggest surprise really is that the interface quality of these materials was extremely good. So we look at a cross-section of a stack like that, really the interfaces are not always clean, but we always find regions which are extremely clean and atomically sharp. And of course, the other thing which we also realized is that we can also misalign these layers. So we can take different layers with different crystallographic orientations and stack them on top of another. And on top of that, we can create these super potentials, which we call moiré superlattices. And these moiré superlattices are really just geometrical interference effects. You can take sort of print out these lattices in 3D, and you can rotate them, and it would get the same interference pattern. So this is really a simple effect. And really, I want to contrast this new moiré physics with heterostructures which people were growing over the years. So gallium arsenide is a famous one. And basically, since the 70s, people invented really complicated machines where they were able to sprinkle atom by atom on any given parent substrate, and they were able to grow layers of different materials one on top of another. Because you start here with a simple atom, every time you grow a crystal like that, it inherits the crystallographic orientation of the underlying material, so you cannot do any of the moiré physics. And this is really special here for van der Waals materials. We start with two-dimensional materials already. And so we can really manipulate them with this twist angle, and we can really create these moiré heterostructures. And so for the sake of twisted bilayer graphene, what happens is that this moiré superlattice strongly renormalizes the band structure. And the band structure which we're getting for a twist of 1.1 degrees, so exactly 1.1 degrees, is the magic angle in the system, we get a set of extremely flat bands. And so these flat bands are here at 0 energy. They're in the order of 10 MeV in bandwidth, and they're separated with larger band gaps to higher order bands. And really what this does to the system is that kinetic energy becomes extremely small, the electrons become very, very slow, and the dominant term in the Hamiltonian becomes interaction energy U. So going from a case where graphene has a linear band dispersion and almost relativistic electrons, we're getting into the system where the electrons almost stop and they start strongly interacting. And the other thing which is also very important is that twisted bilayer graphene, if I'm going to analyze the sort of the winding numbers in the mini-Brillouin zones which are created, it also has topological properties. You cannot construct easily one-year functions, so everything is defined by Chern bands. And really, this adds this sort of additional degree of freedom that these bands are topological. And so here we have really a unique system, I think the first time, that has both ingredients. It has strong electronic correlations and interactions, and it has topological properties. So how does the system look like? So those are just a couple of examples of some sort of characterization experiments one can do. So one of very famous experimental technique, which was very successful in this field, is scanning tunneling microscopy, STM. So this is a scanning tunneling microscopy image of a relatively large area of twisted bilayer graphene. So it's 250 by 250 nanometers. And basically, those individual sort of lattice sites which you're seeing, those are not atoms because it's way too big. Those are really, this is really the moiré superlattice. And you can see we can pair them in quite a homogeneous way, of course, but there's, of course, still a lot of disorder sometimes happening in the system. And the other thing which is sort of very indicative immediately, so we can measure the band structure of materials with photo-resolved emission spectroscopy. So this is typical ARPAS data that we had obtained with a group of Felix Baumberger in Geneva. So really, this is the theoretical band structure of twisted bilayer graphene. So these are literally the flat bands which I showed you before. These are the band gaps which develop in the band structure. And really, ARPAS is able to observe these flat bands, and it was also able to reveal sort of the band foldings in the Fermi surface. Okay, so and I really want to contrast sort of this material platform with other materials which showed similar physics. So for example, crystals, right? So crystals which show superconductivity correlations, magnetism, and so on, have been around for decades. So one famous example is, of course, high-temperature superconductor like the cuprates. Here, the lattice sites and cuprates are, of course, on the atomic scale. They're a few angstroms, and therefore the electrons sit really close by to each other, and the interaction energy you get are EV. So here, contrasting this with magic angle graphene, really our moiré lattice site is in the order of tens of nanometers. So this is really an order of magnitude, or 2 orders of magnitude larger lattice site. And of course, then the interaction energy is smaller. It's in the order of MeV. And of course, famously, in Munich, optical lattices are studied quite broadly. Of course, one can contrast this with optical lattices. Here, of course, these systems are much bigger, and interaction energies are even lower, so you have to cool the systems down dramatically. But besides sort of this sweet spot, this interaction in sort of between those two other systems, which I show here, there are also new capabilities you can do with these two-dimensional materials, which you cannot do with crystals, nor can you do with optical lattices. So one thing is, if we go back to sort of a Hubbard model and look at what are the defining parameters of what insulator, of course, this is the kinetic energy T. So this is defining the tunneling between two lattice sites, and this is the on-site energy U, which defines the interactions if two electrons sit at the same lattice site. And it turns out that we can really precisely tune both of those quantities. So first of all, we can tune the kinetic energy. So we have, many people who did early on band structure calculations, they found that really the bandwidth of these flat bands is extremely sensitive to the exact twist angle. So this is sort of showing the density of states peaks as a function of twist angle. And the twist angle is really the density of states, and sort of the bandwidth is the smallest at around 1.1 degrees. But if you move away a little bit in either direction, the bandwidth becomes bigger again, and therefore kinetic energy becomes bigger. So we can really control kinetic energy with this term. And also, onset energy U we can control because we can actually stack up our material in a very complex dielectric environment. So we usually stack our twisted bilayer graphene in HBN. It has a dielectric constant of 3.9, but you can use other dielectric constant materials. And also we have found early on that if you put metallic layers very close to the graphene surface, just really separated by a few nanometers by this HBN, electronic screening becomes important, and you can really tune the interaction strength with this screening layer. So overall, of course, this is a highly tunable platform where the U versus T ratio can be tuned very accurately. And one thing I want to also notice, so those are typical devices that we make. So those are AFM devices. We can measure transport properties, very simple transport properties like longitudinal resistance and Hall resistance of it. But also we can use this metallic layer, which I explained before, so this graphite layer, to apply a voltage to it and capacitively charge up the twisted bilayer graphene. So what that really means is that if we look at the Fermi energy of the twisted bilayer graphene, we can really tune the Fermi energy and control the filling of the bands continuously with any degree of a precision that you want. So we can really study filling dependence of that material very precisely. Okay, so now, since I'm talking about transport experiments, so those are, I just want to show you some phase diagrams which we obtain when we measure transport properties of the system. So this is a device where we measure resistance, RXX, also RXY, which is the Hall density, Hall resistance, as a function of carrier density. So when we tune the carrier density, we just basically sweep the voltage on the electrostatic gate, and we populate and depopulate the electrons. What we can do immediately with this carrier density number, we can translate it to electrons per unit cell, right? So how many electrons or holes do we have per moiré unit cell? So, and this is on the top here. So this is, again, we can tune, because it's a fourfold degenerate system, we can tune to anywhere to 1, 2, or 3 electrons per unit cell. And so what happens here is that you see at a lot of the integer fillings, for example, here and here, we get highly resistive regions. So those are the red regions where resistance is high. And those are really the correlated insulators. I'll talk in more detail about it in a second. Then we have also these dome-shaped blue regions. This is where resistance drops to 0. So those are our superconducting states. And the superconducting states quite often flank the correlated insulators. And I will, again, touch base on this in more detail. Then, again, moving on to another filling, here at filling 1, we see magnetism, and we think it's of orbital and not spin nature. We see Chern insulators, basically topological edge channels when we apply a slightly elevated perpendicular magnetic field. And then in the middle, in the sort of metallic region in the center, we also see strange metals. And really, for the rest of the talk, I'll just try to briefly, like 1 minute per slide or so, try to go into more detail about these states. And let me start really with the correlated insulators. So this is basically one of the sort of highlight measurements that we did, where again we measure resistance as a function of filling, as a function of a number of electrons per unit cell. And you can see, so we start here at the edges where 4 electrons per unit cell are filled. So those edges are the single particle gaps, which I showed you before in the introduction. Those are really explained and understood by a single particle band structure calculation. So those are not exotic, not due to interactions. But all the other peaks you can see here. Again, we see resistance peaks at 1, 2, 3, and -1, -2, -3 electrons per unit cell, exactly at integer fillings. And those are really the correlated insulators or MOT insulators if you want. But because in graphene we have a fourfold degeneracy, we have, in addition to spin, we also have valley degrees of freedom. So we have actually 4 electrons per band. This really means that we get insulators at all the integer fillings, so at 1, 2, and 3. Instead of, like, for a twofold degenerate system, it would be just at 2. And really, the sort of picture in which we sort of naively started to understand the system, of course, now the theory has advanced and the details are slightly more complicated, is really in this MOT insulator picture, where basically electrons in a fully filled lattice like to localize in the lattice sites if the condition that interaction energy is much, much bigger than kinetic energy. So therefore, the electrons don't like to tunnel to the nearest neighboring site because it's costs additional energy. And so what happens now is really that such a situation occurs at 1, 2, or 3 electrons per lattice site. And really, when this sort of condensation happens here, energy gap is formed in the otherwise metallic band. And this energy gap polarizes also and breaks some symmetries of the band. So as I mentioned before, we have 4 degeneracies here. We have spin and valley. So when we open up a gap here, we necessarily break one of those symmetries. So you can imagine immediately by this simple argument that ferromagnetism is an option here. Also, valley polarized states are options here. And in principle, of course, theory is so far now to identify the ground states here. And in all generality, those are, of course, SU4 spin and valley degenerate states. So you break some sort of so these states basically are some sort of states in the SU4 space. Then a couple of words about the superconductivity. So superconductivity was really one of the first things people observed here, and we characterized that ground state quite extensively by now. So really, we can measure all the significant sort of signatures of superconductivity, like zero resistance, with a TC of below 1 Kelvin. In the best case, is 5 Kelvin. We can apply perpendicular magnetic field, kill the superconductivity, and extract the critical magnetic field. From the critical magnetic field the behavior, we can extract the coherence length, which is in the orders of 50 nanometers. We can do nonlinear conductance measurements to get critical currents out, etc. And really, the biggest sort of signature that this is superconductivity are those Fraunhofer interference patterns, which we obtain when we measure nonlinear conductance as a function of current and magnetic field. So in that measurement, we really see these signature oscillations when we create a weak link in the system. So we can basically interrupt a superconductor with a normal region and therefore create Josephson junctions. And these Josephson junctions really are showing us, in these Fraunhofer interference patterns, show us that this is really a coherent state that we're probing. It's not just some zero resistance state. It's really like a macroscopic quantum state. And this is really by far the biggest evidence that this is superconductivity here. What's special about the superconductivity is really that it's the lowest density superconductor ever found. And also, of course, the thinnest superconductor ever found. So on this chart, which shows the thickness and the carrier density per sheet in any given superconductor, magic and graphene has really this sweet spot. It's orders of magnitude lower carrier density. So it's almost at the BC to BCS crossover. It's really a very strongly coupled superconductor at those densities. And for example, if I take aluminum, which is one of the most famous superconductors also for superconducting circuits, it really has something like 5 orders of magnitude higher carrier density. And this is important because in strongly coupled superconductors, people often compare TC to TF. TF is the Fermi temperature. It's kind of proportional to the carrier density concentration. So, and we really get, for the TCs and TFs we get in the system, we get record numbers, which is only comparable to high temperature superconductors. And of course, another sort of early on discussion point was that the phase diagrams of the cuprates of the high temperature superconductors looks somewhat similar to what we obtain in twisted Bilayer graphene when we start with a correlated insulator with some magnetic structure, we dope it, and we get these superconducting domes left and right from it. So I'll sweep that part. So okay, magnetism and Chern insulators. So it turns out that those two effects have more or less the same origin. And this is really, the origin comes from the topological nature of the bands, which I explained in the very beginning. So really, these topological properties are based on the single particle picture of twisted Bilayer graphene. So if you just take the single particle picture and start analyzing the winding numbers in the newly created mini-abelian zones, you find out that they're strongly decoupled. And therefore, unlike in just normal graphene, you get helicities of plus and minus 2 in these mini-abelian zones. And therefore, if you're a theorist, you find it really hard to calculate some linear functions, some localized orbitals for that system. And the system is really defined by Chern bands and topological bands. So by now, the basis is kind of more or less understood. So theorists have obtained sort of these 8 basis states, which have quantum numbers spin, valley, and sublattice. And 4 of these ground states have Chern numbers of 1, and 4 have Chern numbers of -1. So in principle, that means also that under normal circumstances, without any interactions breaking the symmetries here, all those 8 states are perfectly degenerate. And the total Chern number, if you count it up, is exactly 0, so you should not see anything. But luckily, there are ways that you can break those symmetries. So for Dirac nodes, what you need to break is C to T symmetry, so basically inversion symmetry and time reversal symmetry, to lift these Dirac points and open up gaps, which then show these topological properties. And so, for example, what we did and other groups did simultaneously at that time, we were able to break this symmetry by applying perpendicular magnetic fields. So these are typical measurements, again, Rxx as a function of perpendicular magnetic field and filling. And so what we were observing are those diagonal lines which follow the strata formula, from which we can really extract the Chern numbers of these states. So inside these states, of course, resistance is 0 because it's a topological edge state we're measuring. And of course, we can double check with Hall measurements that the energy, so the Hall measurement is also quantized with the corresponding Chern number. So really, this already showed us that really we can reveal this complex topological nature in these states. And as you already see, some of these states, they actually persist to very low magnetic fields, where quantum Hall or like quantum Hall quantization would not explain it. So indeed, in some devices, so here, one of the devices, we really could trace some of these states to 0 field. And this is exactly when we started observing these magnetic states. So these magnetic states, we really understand them as 0 field Chern insulators. So those are basically Chern insulators with topological edge states with a magnetized bulk, which exists at 0 magnetic field just because of symmetry breaking. And you can see here, so really, if we sweep, we measure Rxy, which is proportional to the magnetization in the device, up or down magnetic field, you can see there's really switching and 0 field sort of non-zero Rxy in the system, and the states are almost quantized to HE over squared. So other groups have, after that or before that, there will also work, have shown that these are really perfectly quantized states, so this is really an analogy of the anomalous quantum Hall effect. And so really how you can understand these states is sort of if you imagine something like valley polarization, so that really only the K valleys are populated and not the K prime valleys. And then that gives you orbital currents in the system, again, like quantum Hall effect, but without magnetic field. And this gives us the magnetization. One can, of course, further study this magnetism. One can, for example, do sort of quantum sensing with scanning squids. So people use these scanning squid tips in Weizmann Institute, for example, our collaborators, and they can really locally measure the magnetic field in the device. And really, these magnetic signatures are everywhere, close to the integer fillings. And this is how magnetism looks like in the system. It really looks like you would, like very rich domain wall structures in magnets, and we can even assign Chern numbers to all the different locations here. Okay, so for the sake of time, I'll skip the strange metal. This will take a little bit more time to explain, I think. But really, what I also want to say is that, of course, we have a lot of fun playing with this physics here. It's a really, for me, it took like, I had to basically relearn all my condensed matter physics when we started this topic, because it covers almost any aspect of modern condensed matter physics, from topology, magnetism, superconductivity, and so on. But of course, we also were thinking along the lines of doing something useful with these materials. And so if you're a material scientist, kind of, you always try to think of for some good applications for your materials, right? So one of the applications is related to quantum sensing, in particular to quantum sensing with light. So basically, it turns out because it's such a low density superconductor, it is extremely sensitive photodetector. And so, for example, in this work here, we have integrated a proximatized, so this is a Josephson junction along this direction, this is graphene, and we have proximatized the graphene along this direction with the Josephson junction where we can pass a supercurrent across it. And we can couple that Josephson junction in this resonator based on basically a superconducting circuits platform. And we were able to really measure this device as an ultrasensitive bolometer. So it turns out if we look at the critical current of the JJ, we can use it as a thermometer. So we can use the critical current as a thermometry scheme. And it turns out really that when we inject photons, gigahertz photons, through the waveguide here, we find that this is sensitivities here are in the orders of 100 photons per square hertz. And that means that sensitivities of a single photon at 32 gigahertz frequencies are possible with the system. 32 gigahertz, this is really extremely low energy photons. Again, only found at millikelvin temperatures in dilution refrigerators and in these superconducting circuit platforms. And indeed, such a detector could be, in principle, integrated like a click detector to count single photons in a superconducting circuit experiments. And of course, we also try to use these single photon detectors then to study some photo-clicking events for mid-IR experiments. And really, these JJs made out of graphene are superb single photon detectors. You can really count low energy photons with it. And of course, now we're also doing these experiments with these moiré superconductors, which are also looking very promising now. So before I stop, just one thing. If you're really interested to learn more about this topic, there is a very good summer school, which also is attended in person, but also remotely, so you can just connect via Zoom. And really, this school is all about the correlations in flat bands, and which discusses this system, but also other moiré systems which are being explored right now. And with this, I want to thank you for your attention, and thanks.
Thank you, Dima, for this very nice talk. Maybe I'll start with a quick practical question. So how difficult is it to get 1.1 degrees for the twist angle?
Not difficult.
Not difficult.
We can show you.
Okay.
Yeah. So in a week you'll have it. Yeah.
Okay. So every time one of your students or postdocs fabricates a sample, it's always exactly the right angle?
Look, so it took, surprisingly, it took, all my students can do it. Yeah. First of all, there's nobody who really failed at this. It took them maybe like 3 months, 3 to half a year to be really profound in this. Everybody figured it out in the end, and they tell me it's a 50-50 probability that they hit the right angle now. Of course, it's probably much lower than that, but but anything can go. I mean, it's a long process, right? But I think that what they tell me is 50%. Okay. Okay, but then look, other groups in the world are now trying to automatize this process. So there will, I hope in the next couple of years we'll have better control of this.
All right, cool. Questions? Yes.
Is this on? Yeah. Thanks for a very interesting talk. I have a question about the squid. The data is gone now. It's off the screen, but do you have any sense about whether or not the distribution of these domains is thermodynamic in nature, or if they're tied to structural changes in the moiré pattern?
I mean, when we first started looking at the pictures, it almost felt like it follows some structural lines, right? So when you assemble these materials, there are wavefronts, right? I mean, you stack materials, right? There are wavefronts which run across the material when you stack it, and my intuition was immediately that it kind of follows these strain fronts, etc. So that's what we have really no further structural evidence for this, because I think to really do this carefully, we would need to do some STM on the same device, to look at distortions, but we cannot do this in this encapsulated device.
Yeah,
Yeah.
sounds difficult.
Yeah.
Thank you.
Hi.
Hey.
Did you think about, so if you go to an insulating phase and you then dope it a bit, did you then think about observing quasi-particles in the systems? So basically a dopant that generates excitations in the surrounding lattice and then creates porons, basically.
Polarons. Oh yeah. So right. So I mean, yeah. There's like tons of different polarons. I mean, I just saw like last week a talk by Dmitri. They study also spatially resolved scanning near IR microscopy in the system. They can induce tons of different polarons. Electrons coupled to phonons, electrons coupled to magnons, and so on. So yeah, there's a huge library of polaritons that you can induce in the system. But yeah, of course, it would be even more interesting to look at the sort of interaction-driven states there. Yeah. I think we are not the ones to, we don't have the techniques to study that, but other groups can do it, I guess.
So in the interest of time, let's move on and let's thank Dima again for this nice talk.